Let's talk on how to generate the real-time clock of our project that is internally generated from the 8051 micro. I'm not talking about those popular RTC or real-time clock modules, or sometimes they call it Shield, which is popular among the Arduino environment. Well, this is going to be clear once we see the code, but for now, let's see first the output of the program that we are about to develop. So in here, I let the user to press the power on off switch or the SW9, and that's the time the clock will start counting in seconds, and it generates a minutes and hour in 24 format. And before we go on, kindly subscribe to my channel if you have not done yet. By subscribing, actually, you are helping my channel to grow with more DIY amplifier tutorials. Thank you, guys. In episode 9, we will be using the same hardware as in episode 8. Let's take a look at my presentation on how to generate the real-time clock using the 8051 internal processing, and we will be using the timer and interrupts. These are features of almost every micro, not only on the 8051, including the Atmel AVR and probably some other 32-bit microcontrollers. And the way the interrupt run is on the background, possibly without affecting the normal program flows as depicted in this slide number 2. Take a look at it. We will not be discussing the details of the 8051 timer and interrupts hardware, which is built in inside the micro. What we do here is to utilize it for our real-time clock, and this diagram shows how the timer count and interrupt jump into its interrupt service routine to generate the second, minute, and hour again in 24 hours format. Let me make one step backward by looking at the hardware and why I need an external clock source like the crystal. Our clock source is at 12 megahertz, that is the speed or frequency. It is 12 million cycles per second, but the real frequency is only 1 megahertz since the standard 8051 requires 12 pulses of crystal to have one instruction. And if we go to this slide, we will see how the time is derived from the frequency formula, wherein time is equal to 1 over the frequency, which is when substitute 1 million cycles per second, and we have 1 microsecond. Wow, I cannot imagine that it's really a split a second, but our 8051 micro can able to count it every microsecond, and this is the basis on how to generate a second. How is that, you may ask? Let's see the final slide where we let the micro to count in microsecond running at the background, and when it counts 200 microsecond, it will jump into the interrupt service routine and count 5,000 times. This jumping and counting 5,000 cycles multiply every 200 microsecond will take 1 second, and from there we will now generate a minute and hour. I will touch only the new code for the real-time clock as the other code is exactly the same as in episode 8. Let me start with the compiler directive, wherein I need to do this declaration since we will deal with the precision. Now you will see the dot file for the 8052. That is a register file instead of the 8051. Well, all I can say is that it should be really called 8052 core, but even licensed manufacturer will use 8051 instead of 8052 core. So then the flows goes that way, and just simply use 8051 core instead of 8052 core. Remember There were many semiconductors that utilized that so-called 8051 core, aside from the Intel, the original designer. Hence, the 8051 core is an industry standard microcontroller. Wow, that's kind of archive explanation actually. The next one is to declare the crystal to be used, which is the 12 megahertz. As I mentioned, we need the precision for generating the real-time clock. And finally, we have the compiler directive large, which is necessary to call a subroutine which is outside the 2KB program. We will be using this later on. Let's see the clock configuration. The timer setting, which is a formal in BASCOM 8051 based on the reference manual. Well, we just have to take a look at that reference manual, and we'll see how Mark Alberts, the designers of the BASCOM 8051, presented how to generate a real-time clock inside the micro. The next one is the variables to be used, like the second, minute, and hour, which is in bytes. Now, I need to declare in bytes, which is a range of 0 to 255. This will reduce the memory allocation for the number, where we need only a maximum of 60 for seconds and minutes. But take note that the clock is an integer. It is so because it will hold 5,000, and an integer hold a value from minus 32,000 to plus 32,000, and the 5,000 number is well inside it. I just want to mention that the 5,000 is basically the counter for the interrupt routine, which is when multiplied with 200 microsecond, that will generate to 1 second. And the final part of the declaration is that I need to set them to 0. On the main program, we have the instruction to jump into the interrupt service routine. It's called on timer 0 generate real-time clock. We will see that later. Then we have load the timer 0, which is 200 microsecond, which simply means we load 200. That means 200 microsecond, and after reaching 200 microsecond or counting 200 microsecond, it will jump into generate real-time clock subroutine. The other two instructions are enabled for the timer and the interrupts, so you can use them. And finally, when we want to generate 1 second, we instruct the timer to start timer 0. Alright, here we are at the interrupt service routine, which is basically to generate 1 second from 500 times multiplied by 200 microsecond, that is 1 second. Then we build the minute from 60 seconds and the hour from 60 minutes. And I think it is a self-explanatory. Once you see the code, which you can actually download it. You can find the download link below in the description. And finally, guys, we are now looking at the real-world response on the LCD running on the real hardware. And you can see those displaying are my MMI instructing the user to press SW9 to start the timer. And once it presses, it will start displaying the second counting from 0 to 59, that is 60 seconds. And every minute it will blink the LED and it will emit a beep. Well, definitely we would like to have a kind of reliability how precise our real-time clock, and we can actually compare that from a smartphone stopwatch to qualify it, the real-world response, whether there is a reliability issue or not, and if there is, and it needs to be fixed. Guys, it's the end of my video, and once again, don't forget to subscribe to keep me here at YouTube with more free tutorials and DIY power amplifier build with the Class D amplifier, but also with the Class A and Class AB with the emphasis on front panel design, something that looks better than the normal front panel using the powerful microcontroller. And bye for now, stay tuned, and see you in the next episode.